Good afternoon. Today we're going to be talking about section 3.1, introducing the derivative. And the derivative function, it is a function, is probably one of the most fundamental aspects of calculus and what makes it so different from other types of math that you may have encountered previously, like algebra, trigonometry, geometry, anything like that. Calculus is very different just because we have this idea of the derivative. So let's go ahead and dive in. We saw in the previous video for section 2.1 that we can talk about an average rate of change or an average velocity. So the average rate of change in a function f on the interval a to x is the slope of the secant line. And remember, a secant line passes through a curve at 2 points. So let me quick draw my secant line. I've got a secant line that passes through 2 points, one called x and the other called a. Sorry that that's a little smushed. I really wasn't thinking when I started drawing that. Now, the instantaneous rate of change in a function f at a point a is the limit of our secant slope. So m here stands for slope, just like in y equals mx plus b. M is going to be the slope, and we get the slope of the tangent line, m sub tan, by taking the limit as x approaches a of m sub secant. So the instantaneous rate of change in f at a is the slope of the tangent line at a comma f of a, provided that this limit exists. And there's many reasons why a limit might not exist, as we've seen previously, but provided the limit exists, we have the slope of the tangent line. So again, here's this little diagram where I've got some point x and some point a, and they're separated by a distance h. So maybe it's easier to think of this as a point A and then a point A plus some distance h. So here it is using h as your separator instead of the distance between x and a. So the average rate of change in f on the interval a to a plus h is the slope of the secant line, as we've seen before. And here for x, I've just subbed in a plus h, and then I've got this minus a term. Well, positive a minus a is going to be 0, so we're left with just h in the denominator. And often this definition is a little more useful than other definitions, but you really need to know both of them down into your bones to be able to be successful in this class. The instantaneous rate of change in f at a is exactly the limit of the secant function as h goes to 0. So we're still talking about the distance between those 2 points. When the distance between them becomes 0. So we're interested in what happens there. So let's start with an example. I'm going to give you a function, f of x equals x cubed plus x4, and I'm going to give you a point, 1, 5, and I want you to find the slope of the line tangent to the curve. So here we're going to use or more appropriately, for this problem in particular, the limit as x approaches a of m secant. So let's see this in action. From our most recent definition, I'm interested in the function f of a plus h minus f of a all over h as h approaches 0. So I'm going to plug in 1 plus h, so a equals 1 plus h, into my function and get h plus 1 quantity cubed plus 4 times h. And all of this minus f of 1. And f of 1 is 5, so we just leave it alone. I expand out these terms, subtract 5, and pull out an h. Well, I've got an h in the numerator and an h in the denominator. Those are going to cancel. I'm left with h squared plus 3h plus 7. As h goes to 0, my h squared term and my h term go to 0, and I'm left with 7. So our limit is 7. So we found the instantaneous velocity. Finding the slope of a line tangent to a curve, f, at a point A is a huge concept. Namely, this is the concept of a derivative. And a derivative is the major thing that separates calculus from all other forms of math. So let's talk about it. The derivative of a function f at a point A, denoted f prime of A, is given by the following definition. F prime of A equals the limit as x approaches A of f of x minus f of A over x minus A, or f prime of A is equal to the limit as h of x goes to 0 of f of A plus h minus f of A over h. If f prime of A exists, we say that f is differentiable at a point A. So let's see an example. Let f of x equal the square root of 2x plus 1. Compute f prime of 2, i.e. the derivative of f at x equals 2. We're going to use our first definition this time because we don't know what h is, right? And granted, in the last one we didn't know either, but that's not the point. So we're going to use our first definition. F prime of A is equal to the limit as x approaches A of f of x minus f of A over x minus A. So I have f of x, which is square root of 2x plus 1, minus f of 2. Well, 2 times 2 is 4, square root of 4 is 2, plus 1 is 3. So I've got a minus 3 term. Positive 1 minus 3 is negative 2. So my limit actually becomes the limit as x approaches 2 of square root 2x minus 2 over x minus 2. And clearly we've got a problem. If I were just to plug in the value 2, I would get 2 minus 2 in the numerator and 2 minus 2 in the denominator. So just basically we get 0 over 0, which is a problem. Which means we need to use one of our alternative techniques to figure out how to solve this problem. And that technique is going to be using the conjugate. So I'm going to multiply by 2x square root plus 2 over 2x square root plus 2, because all of this is the same as multiplying by the number 1. When I do that, my numerator is going to turn into 2 times x minus 2 over x minus 2 quantity times 2x, there should be parentheses here, I'm going to draw those in real quick. And the main thing to notice is that my numerator and my denominator both have an x minus 2 terms. That's going to go away, and I'm left with 2 over 2x square root plus 2. Now we can plug in 2, and we get 1/2. So the derivative of our original function f of x at the point A equals 2 is equal to 1/2. This is the exact same concept as finding the slope of the tangent line. Finding a derivative and finding the slope of the tangent line are the exact same thing, and they will be asked in both ways on exams and in your homework.